I'm excited to introduce our next speaker, Hiro Ono. Welcome, Hiro.
Hi, everyone. I'm Hiro Ono. I'm a plant roboticist from NASA JPL. Today, I'm going to talk about the paradigm-changing robotic space exploration, which our robot, EELS, is going to enable. Let's start from here. Impermanence. That's a central concept in Buddhism. Everything changes, and there's nothing more impermanent than modern technologies. For example, the letter, that was the only way to telecommunicate until, of course, Alexander Graham Bell invented telephone. So now we can talk to our friends and family over distance. Yesterday, we had a call with astronaut in the space. That was amazing, right? And now, how Gen Z kids communicate to their friends. They don't care about talking anymore. Just playing, social games until 2 a.m. Right? Setting joke aside. So what about space exploration? Of course, the way we explore space is impermanent, right? It has changed a lot, and it would change. We must change it to keep pushing the boundary of discovery. So where are we at exploration? JPL has sent spacecraft to all the 8 planets of the solar system and many of its moons, which we are extremely proud of. But of course, we are far from done. In fact, there are only 3 worlds, the Moon, Mars, and Venus, that humans have deployed complex robotic systems so far. So what I'm going to argue today is that a new paradigm, robotic exploration 3.0, is needed to answer one of, or maybe some of, the biggest and most fundamental questions of humankind. Are we alone? We, life on Earth, are in 4 billion years of solitude. We don't know if this cosmos is full of life. We just haven't met others yet. Or if this universe is merely a barren extent of space and time with only a single pale blue dot, right? We don't know. We don't even know where we came from. And we want to know. That's why we go to space. So let's look back on how the space exploration evolved. Robotic exploration 1.0, that was in the decade that led to Apollo. And in this decade, we launched 20 spacecrafts to the moon, out of which only 8 were successful. So 1.0 paradigm was basically a fast-paced trial and error, which worked very well for the moon, because it's a great way to quickly learn from your experiences. However, it doesn't work for Mars. Why? It's far, right? It takes 6 to 8 months to get there, and the launch opportunity comes up only once in 26 months, so you cannot simply try and fail and improve every month, right? So we needed to change the paradigm to be a more cautious one. So in the past 3 decades, we launched 14 missions to Mars, out of which 11 were successful. Tremendously successful, I would say. But the point of 2.0 is not just being cautious, right? It's more about incrementally sophisticate our capabilities over a series of missions. On each mission, we build upon the information about the environment of the planet that we got from prior missions. For example, I was a flight software programmer for the Perseverance's autonomous driving capability. It was enormously successful. It renewed the Mars driving record many times. Just keep going. The reason that it was so successful was because we firmly built up on the experiences, information from the past. For example, we used all the driving records from Curiosity rover to validate the sleep robustness. Of course, we used the high-resolution satellite images of Mars to run the Monte Carlo simulation and evaluate the performance of the algorithm. So here's how the 2.0 paradigm works conceptually. It is, again, incremental sophistication. Right? So initially, right, before going there, we know nothing about the environment, the world. So we start from a relatively simple flyby and orbital missions to learn about the surface environment. And as we learn good enough, then next we're going to send a medium complexity, medium risk mission, which is maybe a simple robotic mission and maybe a simple rover. And once we've learned enough about the surface environment, we finally design and send the highly complex missions like Curiosity, Perseverance, and now we are working on the Mars sample return to bring back the rock samples from Mars, from which we might be able to find the evidence of life that might existed 3 to 4 billion years ago. It's amazing, right? So the 2.0 paradigm has been enormously successful for Mars, and I'm so proud of being a part of it. However, we have to ask this question. Can we stick to 2.0 paradigm, or do we need another drastic change in paradigm in order to explore more challenging destinations than surface of Mars? Where are the next destinations, by the way? Right? In other words, where are the best places to look for extant alien life? It turned out to be icy moons of Jupiter, Saturn, and beyond. There are many moons completely covered by ice, and many of them, like Europa, Titan, Ganymede, has ocean below the ice, liquid water ocean. And this one is particularly interesting. It's an icy moon of Saturn called Enceladus. When the Cassini spacecraft went there, it found something very unexpected. Geysers. It's a gigantic geyser that ejects the water from the ocean below into the space, forming a ring of Saturn. So it turned out that this little moon of Saturn, Enceladus, about the size of Texas, has a global subsurface ocean and 4 cracks on ice going through the South Pole, through which the water is coming up. On Earth, wherever there is water, there is what? Life, right? So we wonder, is there anything in this ocean, right? If there is, what are they? Right? Microbes, or could be a giant octopi, or bluefin tuna, or yellowtail, or Atlantic salmon. I know, I'm Japanese, you know. Anyways, we want to figure out, right? So can we just send a little robot going through the crack and get to the ocean and figure out? And then we have to ask a question again, right? Can we do such a mission within the 2.0 paradigm or not? The answer is an obvious no for 3 reasons. Right? One is that orbital reconnaissance of the subsurface environment is simply not possible. 2, the cruise time to outer solar system is extensive, typically more than 10 years. So if you want to send like 5 or 10 missions to there, it's going to be easily a century. And perhaps most importantly, it's not just about one planet, right? It's not just about Mars. There are tens or hundreds of so fascinating places that we want to explore in the future, and we just simply doesn't have time and money to send sequences of missions to each of them. So we somehow get to figure out, change the paradigm without relying on incremental sophistication, and rather how we can send a one-shot mission to such challenging places with complex robotic capability, how we can explore eventually the subsurface ocean Enceladus. That's the question. And our answer is this robot called EELS, the Exobiology Extant Life Surveyor. Snakebot. Looks cool, right? But how this is different, how this guy can change the paradigm. The point is actually not being snake. It's more about being adaptive. So the robots from 2.0 paradigm, like Mars rovers, are great, but not so much adaptive, meaning that their behaviors are designed based on the previous missions and mostly fixed before the launch. As opposed to adaptive robots like EELS, their behaviors can be learned from its own experiences and evolve during a mission. So with such an adaptive robot, we can now enable a one-shot mission to a challenging environment. So here's how robotic exploration 3.0 works, right? Initially, again, we don't know anything about the environment, but then we're going to send this adaptive robot directly into the unknown. And then, because environmental uncertainty is so high, you're going to start with a low-risk, low-complexity task, like just raising a head and look around to figure out the environment. Then, it's going to adapt its behavior to the environment based on its own observation to perform some medium complexity task, like slowly walking around the surface to figure out more. And once it learns enough about the environment, now it adapts again to perform highly complex tasks, like going down the vent. Okay? So I'm going to show you the movie that's going to show how future EELS mission to Enceladus would look like. EELS is going to land on the surface and slither on the ice, find the best opening to get in, and figure out, adapt its behavior to go down the vent, maybe taking a spiral form like this. As it goes down, the geometry changes, so you have to continuously adapt, maybe taking a pencil form like this to go through the narrowest opening of the vent, eventually get to the ocean, look for life. If we find life, that's going to be a discovery of millennia. So that looks great. Now we are working hard. In the past 3 years, we worked hard to turn this vision into reality. We prototyped the robot and extensively tested the robot over a wide range of field environment to demonstrate its versatility and adaptivity. We started from a nearby ice rink in Pasadena, and then, of course, JPL's Mars yard. The robot has 30 DOFs, degrees of freedoms. We fully exploit them to enable a wide range of the motion gates, including bio-inspired ones. It's a boldly AI, the same theme as Josie talked about. And then we brought the robot to snow mountains. EELS is actuated by our 400 Newton meter Outrunner motors, designed and built in-house. It's powerful enough to bring the robot up to 35-degree slope. The robot runs the uncertainty-aware SLAM on board to map the environment and localize itself. Adaptivity requires a smart brain. So our kinodynamic path planner enables the robot to avoid obstacles to find a path. Our risk-aware AI allows the robot to balance the risk and benefit under uncertainty, and the reinforcement learning enables the robot to acquire new behaviors without human in the loop. And we can even turn the robot to a mobile manipulator by putting the gripper at the end of the robot. And of course, the vertical mobility, that's the most challenging one. So we built the second iteration robot called EELS 1.5 that has 4 torque sensors between each joints. It uses proprioceptive control to stably stick to the wall and then climb up. So look at Rohan's face here. Wow! Yes, that was the first time we made it. We made the vertical ascent of the ice wall in the ice chamber. Okay, so here's a great demonstration of the adaptivity. On the left, this is from the Opportunity rover from 2004. When it got stuck in sand on Mars, it took 60 days, 60 Martian days to get out. Why? Like your vehicle, rover has only a single mode of mobility, driving. So when it gets stuck in sand, the only thing you can do is to keep spinning the wheels until, luckily, it could get out. As opposed to EELS, when it got stuck in sand in a Mars yard, it switched to a side winding gate to easily step aside from the sand trap. It's possible because EELS has multiple modes of locomotion. That's the power of versatility and adaptivity. Okay, so our ultimate test took place at the Athabasca Glacier in Canada last September. We spent there with 40 members of the team and 2 robots over 3 weeks, did a wide range of testings. For example, the robot EELS went down, went into, and came back out from a 2-meter deep ice channel semi-autonomously. And also we tested various gates, like leader floor gates, bio-inspired side-winding gates. But the real reason that we went there was this, called Moulins. It's a gigantic crack on ice, 10, 20, even 30-meter deep. It's a beautiful place. And arguably, this is one of the best analog of the Enceladus vents here on Earth. So we put our EELS 1.5 robot in a few of those moulins. Once the robot is in place, it turned on, extend its arms like this, push the walls against each other to hold its own positions, supporting its own weight. And we loosen the rope, and then it uses the screws on the side to go up and down vertically. We made fully autonomous 1.5-meter-ish descent in a natural glacial hole. That was an enormous success. And here's how we celebrate it. Okay, so now I would like to replicate this excitement on the stage. But we could not bring the huge robot and build the ice walls here. I wish I could. So we brought the little sister, introducing Guardian EELS, and the team, the autonomy lead, Rohan Tucker, the co-autonomy lead, and the field lead, Mike Payton, deputy program managers, manager Rachel Etheridge, and system engineer Rich Weaver. Okay, Rohan, take away.
Good. So small robot doesn't necessarily mean small brain. The Guardian EELS is powered by the same Neo autonomy software that we used on the big robot that was deployed at the glacier. In Neo autonomy, we are trying to basically build this new software paradigm for robotic exploration 3.0. And it stands on 3 pillars. We are building all the technologies required to explore unknown worlds with extreme terrains using a versatile hardware. So starting with unknown worlds, we do this by using a risk-aware autonomy formulation. So right now, Mike and Rachel have asked the robot to go up and down, and Rich is making sure that the safety tether is completely slack. So the robot is going up and down on its own. And if you think about the risk that is involved to go down holes, basically if you send one wrong command, the robot completely falls and it's mission over. So the risk sensitivity is very high. We achieve this extreme terrain navigation by leveraging the high degrees of freedom of the robot. This robot has around 16 motors. The bigger one has more. And you can think of Neo Autonomy as the autopilot software for a self-driving car with more than 48 steering wheels and pedals. And it's designed for space exploration. So we know that in space, there are no stop signs, speed limits, or even a road. So imagine trying to control such a vehicle to go down holes, right? What's even a road? What's an obstacle? To answer these questions, we rely on versatility of the robot. So I like to think of this robot as a robotic manipulator with a floating base. And in addition to that, it's a manipulator with 16 end effectors. So every module, every contact point is one end effector that you're trying to push into the terrain. And I like to make the joke that we have robots that can drive on Mars, but none that can clean our kitchen. And that's because multi-finger grasping is still an open research problem. And if you think about what the robot is trying to do over here, it's very similar to you trying to grasp your phone and manipulate it, right? So it's the same problem that's inside out. And in conclusion, Neo Autonomy has developed a lot of technologies that are not specific to a snake robot. These technologies can be applied to any robot to enable robotic exploration 3.0, where you want to explore unknown terrains, where there are extreme environments, where you have a versatile platform with high degrees of freedom. Thank you.
Thank you, Rohan, Mike, Rachel, and Rich. And by the way, we brought our big EELS robot on the lawn. We're going to do live demo today and tomorrow, so please make sure to visit us and see the robot moving on live. So, what are our next steps? Our logical next steps is to bring EELS to the moon, not just because it's for tech demo, but because EELS is going to be helpful for many things on the moon, right? For example, constructing the lunar base. Remember, it could be a manipulator. Or supporting astronaut activities on the moon. Lunar science, maybe delivering Amazon packages on the moon in the future, right? There are 200 things that the robot can do on the moon, but you don't want to send 200 robots, each of which is specialized to one thing, right? Rather, you want to send an adaptive robot like this that can do 200 things. And within my lifetime, I'm 41 now. I think I have 30 or 40 years, if I'm lucky. I definitely want to see the robot going down into the vent of Enceladus to find life. They are mighty things. That's the motto of JPL, which means that we are not afraid of changing the way to explore space. We've already did one drastic change in paradigm from 1.0 to 2.0. And now we are defining the 3.0 paradigm with intelligent and adaptive robot. And 3.0 is not just about Enceladus, right? There are so many fascinating destinations that 3.0 paradigm can enable to access, right? For example, there are caves on the moon, which has important use cases for future human exploration. Mars has interesting lava tubes underground. Some scientists suspect there could be still life over there. Kuiper belt objects, small bodies floating beyond the orbit of Neptune. Maybe we want to catch up with interstellar objects, land on it, sample rocks, and investigate the materials from other star systems. And someday, surely beyond my lifetime, but we want to send a spaceship over tens or hundreds of light years to explore the habitable exoplanets. That's our dream. This is a team. the best and the brightest from JPL. This is a team that is turning the dream into reality. Okay, so we came back to where we started. Impermanence, everything changes. Everything must change, including the way to explore space to keep moving forward as a humanity, right? However, here is my favorite quote from Mr. Bezos. What is not going to change is more important than what is going to change. Is it right? Yes. Okay, thank you. But does this mean that Jeff and I have fundamental disagreement? Probably not, because what drives changes, what drives innovation, is something that never changes. For example, look at the telecommunication 1.0 letter. It's from 200 years old, somewhere from Japan. This says, "Daddy, I miss you." My own parents, old, they are living in Tokyo, Japan, but thanks to new technologies, I can talk to them every week over Zoom. They are so happy to be able to see their grandchildren's face. And yesterday, actually, the astronauts talked about talking to family from space, which is amazing, right? So what drives the innovations in telecommunication is our fundamental desire to stay connected with family and friends. It's about love, right? That never changes as long as humans exist. And same for space exploration, right? Space exploration is relatively new, but what drives us to space is as old as Homo sapiens, something that is written in DNA. I think it is our ardent desire to end our cosmic solitude. We want to know who we are, where we came from, and where we are going to. Are we alone? That's probably one of the oldest questions of humankind. And if we find alien life somewhere in the universe, that will be one of the biggest discoveries of science, maybe on par with Newton or Darwin. That will be forever remembered by our remote descendants. And isn't it extraordinary that such a discovery could happen within our own lifetime? But only if we start this paradigm change right now. And changing paradigm is not easy, as you know. So I would like to invite everyone in this room to join us, join our revolution, to set off to this greatest quest of humankind. Thank you very much.